next quantity we're going to talk about is energy. Energy is also a great way to look at motion. So basically, we're going to look at motion all over again, but look at it from a different perspective. Energy, you can think of, is the potential to make something happen. For example, when you eat breakfast in the morning, that gives you the energy to walk up the stairs and come to class. Or hopefully it does. Energy has different forms. Your food, for example, is a form of potential energy. It's a stored energy. So potential energy is energy that is stored in a system. Whether it be food that you eat that can then be used to make your body move, and your brain to think, or gasoline, for example, is a form of potential energy. You put it in your car, which can then be used to run the car, make it move. Another form of potential energy that we're going to talk about is called gravitational potential energy. If I hold my marker up here, there's the potential for it to move. Now, granted, as long as I hold on to it, it's not going to move. But if I let go, gravity makes the marker fall and hit the ground. There was energy stored in the marker just for the fact that it existed right here. If I let go, it moves. So that is a form of energy. Any object at some distance above the ground will have potential energy. And that potential energy can cause the object to move if the net force is no longer zero. So if gravity is allowed to take over. Another type of potential energy or stored energy is in a spring. I don't know if you've ever played with a spring. If you stretch it out, it has stored energy. Because if you let go of the spring, it will snap back to its original position. So anything that will potentially make your object move is a form of potential energy. So we'll look at potential energy. The energy involved that an object has when it is moving is called kinetic energy. You've heard the prefix "kine" before for motion. So kinetic energy is the energy an object has because it is moving. It's kind of like momentum. Momentum is something an object has because it's moving. Kinetic energy is something an object has because it's moving. Okay? Thermal energy, energy related to how hot something is actually fundamentally the kinetic energy of the molecules within the object. So for example, the air in here, this room has a certain temperature right now. The molecules on average have a certain energy. We would call that the thermal energy. But it's technically a kinetic energy. The little molecules, all the little air molecules are moving around in the room. So thermal energy is a form as well. Radiative energy, that's energy that light carries. Light carries energy. Light can interact with other objects and make them move or exert forces on them. Einstein's famous equation, E equals mc squared, is a concept of mass energy. For example, in the sun, there's hydrogen fusing into helium. It takes 4 hydrogen atoms to make 1 helium atom in the fusion process. Turns out, 4 hydrogen atoms have more mass than 1 helium atom. And so some of the mass is lost. That mass goes straight into energy. And that energy is the heat and the light we get from the sun. So there's a number of different types of energy we're going to work with. Right now, we're going to focus on potential energy and kinetic energy. So we're not going to worry about how hot an object is or whether its temperature is changing yet. We're not doing any fusion reactions, so we're not creating mass energy. We're not worrying about light yet, so we're not worried about radiative energy. So right now we're going to look at potential energy and kinetic energy. Energy actually is a really convenient way to relate distances to speeds without having to worry about acceleration at any point. Way to do this. For example, let's revisit the concept of free fall. So an object, for example, if I threw my marker in the air, as soon as it has left my hand, as soon as my hand is no longer touching it, it is in a state of free fall. Doesn't matter if it's moving up or moving down. Definition of free fall is that only gravity is acting on your object. So once it leaves my hand, it's in a state of free fall. It's not going to be moving fast enough for drag to be significant, so it's okay to ignore drag. So free fall. In free fall, the only force acting on our object is gravity. Force of gravity acts downwards, so I'm going to put negative mg. But according to Newton's second law, that force has to equal the mass of our object times the acceleration of our object, which is why the acceleration is 9.8 meters per second squared pointed downwards if only gravity acts on it. If you solve for a, you get negative g. Now with energy, we're taking time out of the picture. We're not going to worry about how long it took for energy to transform to one form between forms. So we want to get time out of the picture. Time, remember, is in here in terms of the acceleration, because acceleration is the derivative of velocity with respect to time. But I want to get rid of time. And it's not mathematically legal to just cross it out, because I don't like it there. We have to be a little more ingenious about this. So, to write dv dt so that it doesn't depend on time, I am going to multiply this by dy over dy. That doesn't change the quantity. dy over dy would just be 1. Okay? So dy means some infinitesimally small vertical distance. I'm going to flip-flop these denominators. So I'm going to have dv over dy times dy over dt. dy, y is just a position. It's a vertical position. So the derivative of position with respect to time is what? Velocity. So this is basically velocity times dv dy. My time's gone. Now, it's certainly embedded within the velocity, but the variable time is gone from my equation. So in place of dv dt, I'm going to put in v times dv dy. Oh, thank you. Make this big deal about getting rid of t and write it in there. Going to pull the dy to the other side and integrate both sides. So I'm going to have negative mg dy mv dv. Integrate both sides. What's my variable on the left-hand side that I'm integrating with respect to? Y. The dy tells me my variable is y. My limits need to be from some initial y value to some final y value. So negative mg is a constant. Integral of dy is simply going to be y. Plugging in the limits, we're going to get y final minus y initial. What's the variable on the right-hand side? It's what, sorry? V. Exactly right. V, the speed. M's a constant. I have v here, so integral of v, with v being my variable, is going to be v squared over 2. My limits need to be some initial speed to some final speed. So we get 1/2 mv final squared minus 1/2 m v initial squared. So the left-hand side, minus mgy final plus mgy initial is equal to 1/2 mv final squared, minus 1/2 mv initial squared. This is energy. Kinetic energy. We're going to use a capital K to represent it. Kinetic energy is 1/2 mv squared. Now I know there's a mass in every single term here, so if we were to solve a problem, the mass would cancel, which is great. But we need the mass there in terms of describing the actual energy. The amount of energy an object has depends upon its mass. So the kinetic energy an object has depends upon its mass and how fast it's moving. So 1/2 mv squared. The more massive it is, the more energy it will have. The faster it's moving, the more energy it will have. The speed is a bigger player than the actual mass is, since speed is squared. This over here, mgy, that is our gravitational potential energy. That's the potential energy stored in your object because it is at some height y. So gravitational potential energy our book uses a capital U for potential energy. I'm not exactly sure where that came from, but that's what we use. Gravitational potential energy depends upon the mass of the object, the acceleration of gravity, and y being a vertical position. If I have two markers, both at the same height, they have the same amount of energy. They're the same mass, they're the same height, they have the same amount of potential energy. If one's higher than the other, then this one will have more energy than this one will. Okay? But the height. What if I take my markers and move them closer together? That won't make a difference to the potential energy. As long as they're still the same height above the ground, they'll have the same amount of potential energy. That's why we specifically use y in this equation. Okay? The only way gravity can change the kinetic energy of an object is if it's allowed to move the object vertically. Gravity has no effect on the acceleration of the object if it moves horizontally. Right with that? So gravity, for example, can't speed my marker up or slow it down as it rolls across the table, because the table is flat. It's the same distance above the ground the whole time. So there must be something else that made my marker stop. It wasn't gravity. Friction made my marker stop. So friction played a role in changing the kinetic energy. Okay? In the case of free fall, where we only have gravity acting on an object, it turns out this is negative final potential energy plus initial potential energy. That's the final kinetic energy minus the initial kinetic energy. Change. Remember, the change in anything is always the final value minus the initial value. So this side is negative change in potential energy. This side is the change in kinetic energy. If we bring them to the same side, we get something similar to what we saw with momentum. In this case, the change in kinetic energy plus the change in the potential energy has to equal 0. That means if my kinetic energy changes, then my potential energy must change by the same amount so that when they add together, I get 0. This is a conservation of energy equation. Energy is conserved, meaning it stays within our system. As our ball flies through the air under free fall, As its kinetic energy decreases, so if it's flying higher and higher in the air, it's slowing down. If it's slowing down, then its kinetic energy is getting smaller and smaller and smaller. According to the law of conservation of energy, if my kinetic energy is decreasing, that energy must be transferring into some other form. I can't just lose it. I just can't get rid of energy. There's no way to magically create energy. There's no way to magically get rid of it. So if my kinetic energy is decreasing as the ball goes higher and higher in the air, where is it going? Into gravitational potential energy. This term is getting bigger and bigger and bigger. As this gets smaller, that gets bigger. As the ball falls back down towards the ground, this will get smaller and smaller and smaller. This will get bigger and bigger and bigger in relation. Okay? So this is our conservation of energy equation. Similar to what we did with momentum, we can put all the initial stuff on one side and all the final stuff on the other, and say mgy initial plus 1/2 mv initial squared is equal to 1/2 mv final squared plus mgy final. So it tells us the total energy our system has initially, the combination of the gravitational potential energy and the kinetic energy it has, the energy it has initially has to still be there finally in terms of kinetic and potential. An object can have both potential and kinetic energy. It's not limited to one type of energy at any moment in time. So an object can have both types. So, for example, problem we've seen before, or at least similar to what we've seen before. We have a ball thrown upwards at a speed of 12 meters per second. How high does it go? Now we can certainly use our kinematic equations. We know how to use kinematic equations. We've done problems like this before. They're still perfectly valid. You can still use them. But let's approach the problem using energy. So we're ignoring drag. Our ball's in a state of free fall once it has been thrown. So all the potential energy it has initially, plus all the kinetic energy it has initially, has to equal all the kinetic and potential energy it has finally. So let's draw a little rough sketch. Here's our ball initially. It's thrown upwards with a speed of 12 meters per second. We know it goes up, slows down, slows down, slows down until it reaches a maximum height. And call it h. Now, similar to what we did with our kinematic equations, we still need an origin to work from. When we look at gravitational potential energy, the mgy, y needs to be measured from somewhere. So you have to choose a y equals 0 somewhere. You can choose it wherever you want. I'm going to go ahead and say y equals 0 right here. I'm going to put my origin down here at the initial position where the ball left my hand or whatever projected it upwards. So y initial will be 0. Y final will be h, whatever that height is, however high it goes. If I'm calling y equals 0 down here, what can you tell me about the gravitational potential energy initially? It would have to be 0 as well. Exactly right. If it depends upon height, and we've called height 0, then that has to be potential energy 0. Zero potential energy is really arbitrary. It doesn't mean that nothing can move. For example, if we called the tabletop height h equals 0, it doesn't mean my object would fall and stop all the time on the table height. Certainly if it hit the table it would stop. But if I had my object over here and dropped it, it doesn't stop at the table height just because I called it 0. What can you tell me about the potential energy of my marker if I call the table height 0? It'll be negative. Exactly right. The potential energy would just be negative, because y would be negative since it's below the table. Okay, so potential energy of 0 is kind of arbitrary. It doesn't mean that nothing will happen. In nature, objects will always try to get to the lowest possible value of potential energy. So if there's a negative mgy that it can go to, it will go there. Okay. Up here, finally, the ball will have potential energy because it's not at y equals 0. It will have potential energy of mgy, but y is the height, however high it goes. So that's one of our terms. We need to look at the kinetic energy as well. Initially, the ball is moving, therefore it does have kinetic energy. Anything moving has kinetic energy, whether it wants to or not. Its kinetic energy will depend upon its mass and how fast it's traveling. Up at the top, how much kinetic energy is there? 0. At that instant, the ball is not moving, so it will have no potential energy. Well, according to the law of conservation of energy, and because we're ignoring drag rather, whatever energy we start with has to equal all of the energy we end with. So the energy we start with is 1/2 mv squared. The energy we end with is mgh. So those have to equal each other. The kinetic energy the ball started with has to equal the potential energy it ends with. Well, masses can cancel now. So I have v initial squared on this side, and then 2, if I bring the g over, that equals h. So this is a quick relationship between how fast it was going and how high it goes. So 12 meters per second squared over 2 g. .3 meters. That's how high it would go. If you calculated and got anything different, let me know. Questions on getting how high it goes? We okay with that? Now, whether this approach was easier or harder than the kinematic equations is really a matter of opinion. Kinematic equations are really easy to use, so it's not necessarily easier to do it this way. But we'll do some examples where it starts to get easier.
Does this work whenever acceleration is not constant?
It will work even if acceleration is not constant, yes. That's one very fabulous thing about energy, is that acceleration does not have to be constant to use energy. kinematic equation, this acceleration has to be constant to use it. Now granted, in this case the acceleration is constant, it's just that of gravity. But we will look at situations where the acceleration is not, and then it will still work, which is very fabulous. So, second question, referring to the same problem. How fast is the ball moving when it gets halfway to its maximum height? So, when the ball's right here in the middle, it's still moving, otherwise it couldn't make it to its maximum height. So the ball here, let's go ahead and keep the same initial stuff down here, but make this the new final. This is our new final position. So we have gravitational potential energy, because it's not at y equals 0. So the fact that it's above our y equals 0 means we have gravitational potential energy. But the ball is moving still. So the ball also has kinetic energy. So it has both types. As the ball continues upwards and upwards and upwards, the kinetic energy is getting smaller and smaller and smaller, because it's traveling slower and slower and slower. It's not until this instant, when it reaches its maximum height, that the kinetic energy actually goes to 0. So anywhere between the bottom and the top, it has kinetic energy. The only place the potential energy is 0 is at the bottom, where we called y equals 0. So any place above that, it has potential energy. So anywhere between the top and the bottom, it has both types of energy. It's not a problem. You can have both types of energy. It doesn't ruin anything at all. Same approach though. Whatever energy we started with has to equal the energy we ended with. So the 1/2 mv initial squared is what we started with. That has to equal what we're ending with. So if it's at half the height, it has half the potential energy. You right with that? mg 1/2 h is half of mgh. So if it has half potential energy here, then half of it has to be kinetic as well. But does that mean the speed is just going to be half of the 12 meters per second? No, because of the square term. But we can easily find it. Our 1/2s are going to cancel. Our masses are going to cancel. So V initial squared is going to equal GH plus V final squared. So V final will be the square root of V initial squared minus GH. This should look somewhat familiar in terms of our kinematic equations. So V initial is 12 meters per second. Need to square that. G is 9.8 meters per second squared. We calculated H to be 7.3 meters. So the speed halfway up will be 8.5 meters per second. Energy is a fabulous way to relate speeds to heights without worrying about what happens in between. Not worrying about how long it took, not worrying about what the acceleration was. In the case of free fall, energy is pretty much as easy as doing the kinematic equations. So Whether you choose to do kinematic equations or energy really doesn't matter. They're pretty similar. But energy also works if acceleration is not constant. For example, we have a spring. The force a spring exerts on an object depends upon how far the spring has been stretched out or compressed inwards. The force is not constant. It changes. Therefore, the acceleration is not constant. It will also change. Which means kinematic equations would not be appropriate to use in any problem involving a spring. Okay? But energy will work nicely. Let's, for example, let's pretend we have a spring on a horizontal surface. For now, let's ignore friction. So let's say the surface is frictionless. We'll bring friction into the picture a little later. I know, you're so excited. Now, the force that a spring exerts on an object, the equation is equal to negative kx. K is the spring constant. It's a measure of how strong your spring is. The spring constant K has units of newtons per meter, newtons over meters. It's a measure of how many newtons of force are required to stretch or compress your spring by a meter. Okay? K is unique to your spring. As long as your spring maintains spring-like qualities, K will be constant for that spring. It will not change. Okay? The negative sign in the equation is because the spring always opposes what you did to it. If you stretch it out, it tries to pull it back. If you compress it, it tries to push back to its equilibrium position. So the negative sign indicates that it opposes whatever was done to it. So let's say we have our mass connected to a spring, and the spring is connected to a wall. In the position it is right now, the mass is not pulling on the spring and it's not compressing the spring. We call this the equilibrium position. The spring currently is not stretched, nor is it compressed. So it's perfectly happy. It's not going to do anything to the mass right now. By definition, for our equation here, x has to be 0 at this equilibrium position, because the spring is not exerting a force right now. It cannot exert a force on something unless it's been stretched or compressed. If it's not stretched or compressed, F has to be 0. The only way to get F to be 0 is if x is 0. So by definition, x equals 0 has to be the unstretched or uncompressed position of the spring. If we take our mass, let's say we pull it out, that's going to stretch the spring out. Well, now the spring is exerting a force on the mass. The spring is exerting a force to the left. It's trying to pull the mass back to equilibrium. Of course, there's a normal force and a force of gravity as well. But because it's sitting on a floor and because there's no friction, they're not affecting the motion of the mass at all. The mass is just going to move along the horizontal surface. The spring, we call it Fs, is the only one that's going to accelerate the block and make it move. Well, similar to what we did before, the spring is the only force acting on our object in the x direction. The x direction is the direction our mass will be moving. You okay with that? The mass is only going to move along the x-axis. It's not going to move vertically. There's nothing pushing it up or down. So the only force causing the acceleration is the force of the spring. So negative kx has to equal ma. But a is dv dt. Again, in terms of energy, we want to get the time out of the picture. In this case, since my object is going to be moving along the x-axis, I'm going to write this as dx over dx instead of dy over dy. In free fall, the object was going to move vertically. In this example, our object is going to move horizontally. So I'm just going to call it dx over dx. Again, if I flip-flop the denominators, I get dx over dt times dv over dx. But dx over dt is the speed. So plugging that in here, we can write our acceleration in terms of speed and the derivative of the speed with respect to position. I'm going to bring the dx to the other side and integrate both sides. On the left-hand side, our variable is x. So our limits need to be from some initial x position to some final x position. K is a constant, so I get negative k. Integral of x is x squared over 2. So I get x final squared over 2 minus x initial squared over 2. That's my left-hand side. My right-hand side, my variable is v, so it's from some initial velocity to some final. We get the same thing on the right-hand side. mv final squared minus 1/2 mv initial squared. This is still kinetic energy. Turns out, if you integrate any of your forces with respect to position, they're always going to equal the change in kinetic energy. Over here, we get negative 1/2 k x final squared. Negative times a negative is positive, so positive 1/2 k x initial squared. The left-hand side is our potential energy. Okay, springs, they store energy in them if they are stretched or compressed. We call this elastic potential energy. We still use a U because it's still potential energy. For any type of potential energy, regardless of what it is, we use a capital U. If you want, you can put a little subscript of an S or something on it so that you remember that it's for the spring. The potential energy stored by a spring is equal to 1/2 kx squared. This was derived from the fact the force was equal to negative kx. X equals 0 at equilibrium. Whether we're talking the force or the energy, x equals 0 at equilibrium. Okay? What this equation tells us, we basically get, again, 0 is equal to negative delta k plus delta u. As the kinetic energy increases, the potential energy will decrease by the same amount, and vice versa. If the potential energy is increasing, the kinetic energy will decrease by the same amount. This equation is perfectly valid as long as you only have a spring that's causing your object to accelerate. Now the acceleration is not constant, because the force is not constant. So kinematic equations cannot be used if you have a spring. It's just not possible. But energy doesn't care. We already took into consideration the acceleration as v dv dx. We've already integrated. We've already taken into account that the acceleration changes. This result will be valid. Even though the acceleration is not constant, it doesn't matter. This result will work just fine in relating our potential energy to our kinetic energy. If we write it out like we did our other equation where we put all the initial stuff on one side, and set it equal to all the final stuff, this equation will work nicely looking at a spring. Now this assumes only the spring is acting on the object in terms of accelerating it. This isn't correct if our spring, say, launches an object vertically. It's not correct if friction is in play. But that's okay. So right now we're looking at a frictionless surface. Let's say we've pulled the mass to the side, a distance of 20 centimeters. Let's give it a mass of 2 kilograms and a spring constant of 150 newtons per meter. How fast will the mass be moving when it reaches the equilibrium position? So I pull it to the side and I let go. When I let go, the spring is going to pull the mass. It's going to try to get it back to equilibrium. Why doesn't it stop, by the way, at equilibrium? It has momentum. That momentum is going to keep, well, the momentum will change because of the force. But the fact that it has momentum will keep it going. You can look at it in terms of energy. It has energy, so it's going to keep going. Without any friction, this mass would bounce back and forth forever. Just keep going and going and going. So let's find out how fast this mass will be going when it reaches this equilibrium position, what its speed will be. So similar to what we did with our last problem with gravitational potential energy, let's call this, where the mass is right now, our initial point. Will there be any potential energy at this instant? Yeah. The spring is stretched. The spring wants to pull on the mass and get it back to equilibrium. So there is initial potential energy. X initial is the 20 centimeters. What about kinetic energy? So I'm holding on to it and then I'm going to let go. So at that instant, is it moving? No. So at that instant, it does not have any kinetic energy. Finally, is when the mass is here. Will there be any potential energy now? No. At that instant, at that equilibrium position, that is defined as x equals 0. If x is 0, there can be no potential energy. If a spring is not stretched or compressed outwards, it will not store energy. So at that equilibrium position, the potential energy will be 0. But there will be kinetic energy. The mass will be moving. So all of the energy we start with has to equal all of the energy we end with. So we start with elastic potential energy, 1/2 kx squared. At the instant we are calling our final position, we only have kinetic energy, 1/2 mv squared. So the 1/2s are going to cancel. Looking for v final, I need to bring the mass over. Take the square root. That will be our final speed. That will tell us how fast the mass is moving at the equilibrium position. It doesn't tell us the direction the mass is moving. I guess I kind of missed that side note. Energy is a scalar. It doesn't have a direction associated with it. You have energy or you don't. It can be positive or negative in terms of gravitational potential energy, but that's just due to your reference point. Energy is just a scalar, which is really nice because we don't have to break it into components. In this problem, we said K was 150 newtons per meter. X is 20 centimeters, so 0.2 meters. Mass, 2 kilograms. So the speed of this block would be .7 meters per second. So energy is very nice. It's an easy way to find the speed. It won't tell us the direction though. But we know the direction just by looking at the picture. We know the mass will be moving to the left. But it will not tell us, energy itself will not tell us the direction. One other side note really fast. Units of energy. For example, 1/2 kx squared. The k has units of newtons per meter. X will have units of meters, but x is squared. This meter cancels with one of those, and we get newtons times meter. If we look at kinetic energy, 1/2 mv squared, we get newtons times meter. If we look at gravitational potential energy, mgy, we get newtons times meter. This we call a joule, and we use a capital J to represent it. So energy is measured in joules, which is the same thing as a Newton times a meter. Which is the same thing, remember Newton is kilogram meter over second squared? So this is the same thing as a kilogram meter squared over second squared. Okay. Calories is another form of another unit of energy. You can convert between calories and joules. We really won't use calories in this class, but it is another form of just a different unit measurement of energy, basically. Questions on coming up with our answer here? Please keep in mind, between this initial spot and this final spot, the mass will have both potential, well, the system will have both potential and kinetic energy. At the instant where it's at its maximum extension and not moving yet, at that instant it only has elastic potential energy because the spring is stretched. At the instant it's at equilibrium, it only has kinetic energy because the mass is not stretched or compressed. But everywhere in between, it will have both types of energy. It will have both potential and kinetic. That's because the spring will still be stretched some, and the mass will be moving. So both types of energy exist everywhere between those 2 points. So energy is a really fabulous way to relate some sort of distance to speed without having to worry about whether or not the acceleration is constant. We've already taken into consideration the force and the fact that it changes in solving for the potential energy. That's done. We're good. You don't have to drive it again, unless you have a different force equation. If you have a different equation that describes the force, you have to integrate that equation to find out what the potential energy will be. Okay? Anytime your force causes the energy to change between potential and kinetic, we call the force conservative. a conservative force, the energy always stays between potential and kinetic form. It doesn't change into, say, thermal energy, making something heat up. It doesn't turn into sound energy. It stays in the form of stored energy, which can then turn back into kinetic energy again. Anytime you can go back and forth between potential and kinetic and not lose any of the energy to other forms, the force is conservative. Notice the potential energy here. When we say that the potential energy plus the kinetic energy change is equal to 0, what if I were to analyze looking at this point where it went all the way over and then came back to this point? The final values would be the same as the initial values were, right? There would have been no change in potential energy overall. But the object moved. The potential energy turned into kinetic energy as it sped up. The kinetic energy decreased as it turned back to potential. Then it turned back to kinetic. Then it turned back to potential. The overall change in potential energy here doesn't really matter if it moved or not. The potential energy only depends upon how far the spring is stretched or compressed. That's another thing that makes it conservative, is that it doesn't matter whether it just stayed there or if it moved and came back there. The potential energy change is still 0. Whatever the kinetic energy gained, it decreased back down and went back to potential energy. Okay. If, or when, we take into consideration friction, will that still be the case? Will it be able to come back to its original position? No. Friction is going to take some of the energy and turn it into a form other than potential and kinetic. It's going to turn it into thermal energy. The tabletop between the block and the table would get a little warmer. Energy is still conserved, but it's not in the form of potential and kinetic energy anymore. This won't be able to equal 0 anymore when we talk about friction. Friction is a non-conservative force. It takes energy away from the system. It does not keep it in the form of potential and kinetic anymore. It changes it. It's still totally, the total amount of energy still stays the same, but it's not in this form anymore. It changes into a different type of energy. But the nice thing is, it's really easy to manipulate this equation to make it work. So, accounting for friction won't be too hard, actually. Okay. So energy, really, most people really like energy once they've practiced with it for a little while, because it's not a vector. You don't have to worry about what direction things are moving. And it doesn't matter if your acceleration is constant or not. So it works quite nicely in all those situations. So we'll do more examples with that tomorrow.